a lot of this is review from Algebra 2, but, you know, review is one of those things where you kind of remember some of it, but there are some pieces that you have to go through. For instance, long division. Those of you that have done the assignment, or those of you that are thinking back to long division, would you agree with the statement, polynomial long division is not difficult, it's just a lot to keep track of? Yeah, that's it. It's not the hardest thing we've ever done, but there is a lot going on when you do polynomial long division. And the division algorithm is something that we use with the synthetic. So how many of you were like, yes, synthetic, I remember that. It was fun and it was easy. So raise your hand if you love the synthetic part. Yeah, I was thinking synthetic is like math magic. It truly is just an easier way to eliminate all of those variables. So we would love to do it all the time if we possibly can. The problem is it has to have a divisor that's in that format of x minus h. So something where it says divide by 2x plus 1, can't use synthetic. We have to do long division. And today we're going to talk about remainder and factor theorem. No, actually that was in the notes. So yesterday's remainder and factor theorems. Use the rational zeros theorem. Definitely going to be talking about that today. And the upper and lower bounds. So lots of synthetic. It's called synthetic substitution. It's called synthetic division. It just matters what you're using it for. And let's see, we've got to. Yeah, this part down here. So in the notes that I recorded for you, what I needed you to see was, first off, we know the degree of the polynomial, or we should be able to find it, and then we should know how many zeros it has. But how many that we can find and what types depends on a lot of things. First of all, something like 4x squared minus 9, that worked out, bless you, all nice and factorable. Hey, we're going to have two real zeros. They will be rational because remember the root word of rational is ratio. And that means something that you could write as a fraction. And that one would be negative 2 halves and positive 2 halves. But if you get a zero like 4, that's still considered rational because you can write it as 4 over 1. So they're the nice ones, you know. And sometimes we might have trouble finding them, so we'll grab the graphing calculator and we'll graph it and we'll find the zero. We need to recognize numbers like 1.33333 when we see it as, hey, that's 1 1/3. And I'll change that to 4/3 and that'll make this rational. And so one of the things we're going to do today is investigate, hey, is that a fraction that I know, or is that something I'd have to do a little algebra for? And then the other thing I wanted to remind you of is that we can get irrational zeros, and you saw in the video that I did not factor this to get the zeros because we wouldn't. We would add 2 to both sides, and then we would take the square root because we're not used to factoring with radicals. We just don't do that. So we get to this point and we realize, well, that means it was x plus the square root of 2 and x minus the square root of 2. But here's the big deal. They always come in pairs. So if you see one radical, you're going to have a second radical. So if the book says one of the zeros for this function is the square root of 7, you are supposed to automatically know, oh, that means negative square root of 7 is there too. They might not give you the second zero. And that's because our irrational zeros, well, you can think about the quadratic formula. Remember, it's plus or minus the square root of whatever. So we should have 2 of them. Imaginaries also come in pairs. We're not going to deal a lot with imaginaries in here, but I need everybody to remember that any imaginary numbers, if we had 1 plus 2i, 1 minus 2i would be its conjugate, which would be the pair of zeros that we would have for imaginaries. So just keep that in mind as they say write them or they say find them all. We have to make sure that we realize which of these are going to come in pairs in every situation. And that's going to be our irrationals and our imaginaries. So on the next page, we have the rational zeros theorem, which you learned in Algebra 2. And this could really be called the possible zeros theorem, because if we don't know what the zeros are and we just want some things to try, that's where we get it from. So it says, suppose f of x is a polynomial function of degree n greater than or equal to 1 of this form. F of x equals a sub n, x sub n. We've seen that before. We know it just means it is in descending order. We've got the standard form polynomial. with every coefficient an integer, and that constant is not equal to 0. So we have a constant in that. If x equals p over q is a rational zero of f, so any generic fraction p over q have no common integer factors other than plus or minus 1, then p is an integer factor of the constant coefficient, a sub n, and q is an integer factor of the leading coefficient, a sub n. Last year, we went through this and said, okay, that's a lot of blah, blah, blah. So what are they saying? They're saying take any of the factors of the constant at the end and divide it by any of the factors of the leading coefficient. And that's a list of possible zeros, things that might work when you go through and find your zeros. Now, we're going to use that, but we're also going to use our graphic calculator to narrow down the search. So reminder, always try to factor out a common monomial factor before you apply the rational zero theorem. So if you see the whole thing is divisible by 2, take the 2 out first. Make your life a little bit. The whole thing is divisible by 2. Take it out, make your life easier. So this next one says, finding the rational zeros. Find the rational zeros of f of x equals x cubed minus 3x squared plus 1. So the first thing we really should do is write down a list of possibles. And again, that comes from all the numbers that would divide into that constant nicely. Well, that's a short list. Plus or minus 1. That's it. And then you divide that by all the factors of the leading coefficient, which in this case is a 1. So we have 2 different zeros to try. 1 divided by 1 is going to be 1, and positive 1 divided by negative 1, or vice versa, negative 1. Those would be the 2 possible zeros that we could try. So we do try them. And we do this synthetically. The other thing I was thinking is it's so weird that this is a Pearson book, because in your Pearson book for Algebra 2, when they did synthetic, it didn't look like this. It looked like this instead. They kind of did the upside down division symbol. I'll take it either way. I mean, if you're not getting used to the new method, feel free, you know. You just have to be able to do the synthetic, and it's the numbers that I care about, not necessarily the way that you write it. Now with this one, I have to make sure it's in standard form, and if anything's missing, I need some zeros. I've got an x to the third, an x squared, oh, no x. I'm going to have to put a 0 in place for the x, all the way down to the constant of 1. So 1x third, negative 3x squared, 0x, and 1, all the way down to the constant. It has to be present. If it's not, you put 0. And then we do what we're supposed to do with synthetic ifs. It's not called the leading coefficient for nothing. We're going to start with that. So we bring down the leading coefficient. If we're outside the box, we multiply. And then we go inside the box. And when we're inside the box, we add. And we just keep oscillating outside, inside, outside, inside. So outside the box, multiply. Inside the box, add. Outside the box, multiply. Inside the box, add. Outside the box, multiply. Inside the box, add. Well, it's not a 0. It didn't work. If this last number comes out to be 0, then it's a 0. Didn't work. Well, we still have one more to try. Negative 1. Let's try negative 1. So same coefficients. And we'll just start over and see if it works. So bring down that leading coefficient, multiply outside the box, add inside the box, multiply outside the box, add inside the box, multiply outside the box, add inside the box. Is negative 1 a 0 this function? No. So we did all of that, and our 2 possible rational zeros don't work. What's that supposed to tell us? That this doesn't have any rational zeros, because we tried the 2 that are possible. So no rational zeros. Now, just to make sure, we definitely would pop it in the graphic calculator. We don't want to write down no rational zeros and then realize we messed up. So we pop it in and see what those zeros look like. So we have x to the third minus 3x There's zeros right there. It's saying they're not rational. That means it shouldn't be a fraction that we can recognize. So second trace, number 2, below it, above it, enter. Yeah, that's not a fraction we would normally know right there, or a radical or anything like that would pop into our head. Negative 0.53208889, no. Second trace, number 2, go after this one. 0.652703. I don't know what that is. That is not a recognizable fraction right there. Second trace, number 2. 2.8793852. So they're probably some kind of nasty radical things. They're real. We can see that. But they're definitely irrational. So we were right. There aren't any rational zeros. Something like 0.5 pops up there. We better know that's 1/2. 0.2, hey, that's 2/10. So 1/5 is one of my zeros. 3. Oh, that's going to be 1/3. You know, those are the things that we're supposed to recognize. But if we look at it and go, oh my goodness, never seen that before, then it's irrational. So we know it has 3 zeros. We see the 3 zeros. They're just not nice ones. They're not nice fractions, so no rational zeros. This one says just, hey, find them, you know, see what they are. Find the rational zeros of f of x equals 3x cubed plus 4x squared minus 5x minus 2. And I realize, okay, my possibles are going to come from plus or minus 1, plus or minus 2, because those are the factors of -2 in fact. And my denominator is going to come from that 3, plus or minus 1, plus or minus 3. So, in the old days, we would write down this list. 1 divided by 1 is 1. 1 divided by 3, 1/3. 2 divided by 1 is 2. 2 divided by 3 is 2/3. And this would be considered a pretty easy problem because there's only 8 numbers that we have to try to see whether or not they're really going to work. Sometimes we'd get up to 20 or 24 different numbers to try. And because we didn't have calculators back then, we just had to do them all by hand, synthetically. You know? And generally our homework was 4 problems a night. That was about it because it took forever to find them. Well, we don't live in that age anymore. You know, now we all have graphic calculators. So we're going to use that to our advantage. And we're going to say, okay, great, those are my possibles, but rather than do them all, I'm going to check it out. See which ones I should try. So 3x to the 3rd plus 4x squared minus 5x minus 2. Right, looking good. Right. Oh, looks like -2 might be right on the dot, and maybe 1, 0 also. So I'm just going to look at the table for those and check that out. Yep, -2, 0, and 1, 0. And that other one, though, second trace. Let's see if we recognize this fraction. Is that something we're supposed to know? What's that one? -1/3. Yeah, so we're going to write that as -1/3, not the decimals. All right, so my possibles are narrowed down. I know it was supposed to have 3 zeros because it's a degree 3 polynomial, but I'm not done. And that's because it didn't say grab your graphing calculator, punch these in, and see whether or not they work. And I punch stuff wrong into the calculator all the time, and I'm sure so have you. So we have to verify this algebraically. The good news is it's just synthetic. That's all it is. You can verify the zeros synthetically. So it doesn't matter which of the numbers you start with. Most people will do the nice integers first and then see what happens with the fraction. So 3, 2, 1, 0, they're all there. And bring down that leading coefficient and then just start your process of synthetic division. So this is -6, adding, get -2, multiplying, get 4, and -1 when we add, and then a 2, and we go, yes, got it. So now I know my math, my algebra matches that. Now, because that worked, I'm just going to continue So I'm going to use my 1 in this result. Let's see what happens. Now I'll bring down the 3. I will multiply, add, multiply, add. Get that? Verified, negative 2 and 1. Now if I don't want to do synthetic with a fraction, maybe I just say, well, I can show this one algebraically. Remainder constant x. So this says 3x plus 1 equals 0. Subtract 1 from both sides and divide by 3. Okay, there's my algebra verification that this works. Not that doing synthetic with negative 1/3 would be difficult. It's not. You don't have a whole lot to work with here. But just so you know, if you get down to the point where you're like, okay, I have run out of things that I can do and I need more zeros, well, it's quite possible you have some more that you can find in that position on. And of course, this is just going to be a sketch of what we saw in our graphic calculator when we went through it. Now, the last thing we should do is we should actually write these down as ordered pairs and say, well, negative 2 worked, so negative 2, 0 is good. 1 worked, so 1, 0 is good. And then negative 1/3 worked, so that's good. There's also one other way to write this that's totally acceptable, and you'll find that they kind of interchange this notation. Sometimes they'll write the answers like this, but other times they'll do this. F of negative 2 is 0, F of 1 equals 0, and F of negative 1/3 equals 0. Both of those say the same thing. It's just what are you using them for? This is just the language to say, hey, this is zeros. This is finding those x-intercepts. And most of the time we'll probably just have you write them as ordered pairs. But know that that stuff it's the same. So if somebody had asked in first hour, like, well, do they all go nice like this? You get down here and you read it off and it's remainder constant x. Is that as high as it goes? No, because if the last couple of zeros are going to be irrational, if they'll have square roots in them, you'll probably have remainder constant x and an x squared. But that's okay, because even if there's an x squared, once we write that polynomial, we could solve it by completing the square or the quadratic formula, either way. And here, of course, we're going to do it by completing the square. But always use the nice ones first and work your way down to the ugly ones, and then figure out how am I going to get those ugly zeros that I have left. So here, this one says, let's not forget that the goal here is to use this math. Maybe some engineering problems where we're trying to make things show up that we need. Interesting situation, something I didn't really think we'd ever deal with in Minnesota. There's a sinkhole on 694 right now. I think it's going to be closing 694 over by White Bear Lake for approximately 8 days. A water pipe broke, and it dug a great big sinkhole out beneath the highway. And it just went down. So nobody was hurt. Thank goodness. Recently, there was another sinkhole in the news where somebody was just walking around and they're walking with their friends, and all of a sudden they're gone, and their friends look back, and the friend dropped down through a sinkhole. They just happened to walk at exactly the wrong place at exactly the wrong time. So that's a Florida thing mostly. We don't see that stuff in Minnesota very often. But lucky us, it's happening right now. Extra example, write a polynomial function of degree 3 with a leading coefficient of 2 and zeros at 5, 4, and negative 1. Now, hopefully when you read through this problem, you said, well, I know exactly how to do that. We've done that in class before. The thing you wouldn't like is this. What do you mean leading coefficient of 2? We've always had a leading coefficient of 1 before. Well, then use your algebra instincts and say, well, this is how I know I would start. I would have to use these as my zeros. I've got a label that says polynomial function, so f of x, g of x, whatever. But I'll have x minus 5, x minus 4, and x plus 1. All right. So, well, we know what to do with that. We've got to multiply all that stuff together. So we multiply the back two together by FOIL. So first times first, x squared, outside times outside is 1x, inside times inside is minus 4x, so negative 3x, and then negative 4 times 1 is negative 4. Then what do we do? We're not done yet. Yeah, you're already doing it. What are you doing? Distribute, yeah, both the x and the negative 5. So let's see if we all get the same thing in the end. F of x equals x to the third minus 8x squared plus 11x plus 1. So here's the last thing that we have to deal with, and it was that new piece. How to get a 2 in front of that x cubed? Can we just pop a 2 in front of the x cubed? No. Well, this is algebra. Would it be okay if we multiplied everything by 2? That we can do. That we can do. Because we would factor it out if we were trying to find the zeros anyway. So all we do is multiply by 2. Because it's equivalent. If we multiply the whole thing by 2, it's equivalent. And again, if we were working backwards, what we would do is we would divide those 2 out first, and then we'd find exactly the same zeros. Except we want it to look like a polynomial function, which means we really should distribute that when we're done, so it's in that descending order when we go through. But that's the thinking, yeah. Is, we're really distributing that to everything that's in there. So that's, like I said, it's kind of, I guess, a common sense thing where you go, you know what, here's what I know what to do. So let me start with that. Now, how do I get a 2? Well, I can multiply everything by 2. It'll still have the same zeros when I get done. And there it is. So we're not done with finding all the zeros, but I need you to remember that writing them is important. Like I said with the sinkhole thing, their whole problem is this. It's now getting to be winter in Minnesota. It's supposed to rain/snow today. They would love to fill up that sinkhole with cement. However, they can't because the temperature has to be at a certain spot to use cement. So they're just going to have to fill it up with tar for now. And that's all from engineering. And we someday, I really, really hope that lots of smart people like you are doing the engineering. We don't want people that don't know what they're doing as far as math goes doing engineering. So we want to make sure that we can do all this good stuff. Now the next piece to our objective today is talking about those upper and lower bounds. And it says we narrow our search for real zeros by using a test that identifies upper and lower bounds for real zeros. A number k is an upper bound for a real zero of f if f of x is never 0 when x is greater than or equal to k. On the other hand, a number k is a lower bound for the real zeros of f if f of x is never 0 when x is less than k. What on earth are they talking about? They're saying these are all the zeros of this function. If you stop at d, you will never find any more zeros. This graph is going up forever. So it's never going to come back down and give you another 0. For the lower bound for the zeros, we're talking about the same thing. We're saying after you go that far to the left, you will never find any more zeros. It's not going to wrap around and give you another 0. It isn't going to happen. So this is our upper bound and our lower bound, which means the zeros are on the interval from C to D. That's where they are. Don't need to bother trying to look for any more because that's where they are. I don't know about you, but I would like to have a way to check that. And that's what we're going to do next, is by algebra figure out, hey, is this really the cutoff for my zeros? And so that way I don't have to look for any more. And we have to do each one of those sides, the upper bound and the lower bound. So upper and lower bound test for real zeros, it just involves synthetic division. That's all it is. So let f be a polynomial function of degree n is greater than or equal to 1 with a positive leading coefficient. Suppose that f of x is divided by x minus k using synthetic division. If k is greater than or equal to 0, well, that's positive. We would want to see, is that an upper bound? Every number in the last line of your synthetic division is non-negative. Now, what they mean by non-negative is 0 gets to count for both, because 0 is neutral. It's not positive or negative. If every single number, when you've done your synthetic, is non-negative, so it's positive or 0, then you have found the upper bound. There's no more zeros that can be found as you move to the right forever. If k is less than or equal to 0, so you're trying to find that lower bound, and the numbers in the last line are alternating, negative and non-positive. Again, what they're saying is 0 counts as both. So it should go positive, negative, positive, negative, positive, negative, where 0 gets to count as both negative and positive. Then you found the lower bound. So upper bound, all positives. Lower bound, positive, negative, positive, negative, positive, negative, where 0 gets to count as both. So what we're doing is we're trying to see, have we found them all? You know, if we found the zeros between negative 2 and 5, did we get them all? Prove that all the real zeros of f of x equals 2x to the 4th minus 7x to the 3rd minus 8x squared plus 14x plus 8 have to lie in that interval from negative 2 and 5. Well, if 5 is the upper bound, when I do synthetic with 5, I should see all positive numbers or 0, because 0 gets to count both ways. So 4, 3, 2, 1, 0. Everything's there. I don't need any zeros for placeholders. 2, negative 7, negative 8, 14, and 8. And I'm just hoping they all come out to be positive. So I bring down my leading coefficient, I multiply, and I add. I multiply, and I add. I multiply, and I add. Multiply. So I was just thinking it doesn't really matter. I know it's going to be positive anyway, but we really should show the right math as we go through there. So I know that's the upper bound. 2, 3, 7, 49, and 253. Those are all positive. So 5 is the upper bound. We're not going to find any more zeros to the right of 5. All right, now I have to make sure that negative 2 is the lower bound. We use the same coefficients from before. 2, negative 7, negative 8, 14, and 8. And see what happens when we do synthetic. So outside the box, you multiply. Inside the box, you add. 2, negative 11, 14, negative 14, 36. In order to be a lower bound, it has to go positive, negative, etc. Positive, negative, etc. Yeah, negative 2 is the lower bound. And just to give you a quick peek at the graph there, you know, graphically we would see, yeah, we've got an x to the 4th. 1, 2, 3, 4. Count them all. They're between negative 2 and 5. That's where those zeros are. Now I know it said prove, but this is an algebra proof right here. We just used algebra to figure out that that is the interval, upper bound and lower bound. Down here it says, let's put all of this good stuff together. Example 7 says finding the real zeros of a polynomial function. So, first question would be, how many are there supposed to be? Should be 4. Now, we are not guaranteed that they are all real. So, remember imaginaries come in pairs. We might find 2 reals and then we might find 2 imaginaries. Might all be imaginary for all we know. You know, we're just starting out, we're not sure. But I do know my list of possibles. I've got an 8 in the back. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And then I have a 2 in the front, which would not factor out. I can't pull the 2 out of everything. So plus or minus 1, plus or minus 2. And that would give me a nice little list to get started with. 1 divided by 1, 2 divided by 1, 4 divided by 1, 8 divided by 1. Then I go back and divide by 2, so I've got plus or minus 1/2. But 2 divided by 2 is 1, which is already on my list. 4 divided by 2 is 2, which is already on my list. And 8 divided by 2 is 4, which is already on my list. So there's my list of possibles. But again, we live in an age where we have graphing calculators. So why do them all if we don't have to? So let's see if we can get some nice zeros from this. 2x to the 4th minus 7x to the 3rd minus 8x squared plus 14x plus 8. Make sure all that's in there, right? Graph. So, looks like maybe one of them is nice here. Not a whole lot of them. Let's check it out. Second trace, number 2. I'm going to go from left to right. So, I'll try this one first. Negative 1.414214. You recognize that as a fraction that we're supposed to know? Well, then we better look at the other ones and hope they're nicer. So, second trace, number 2. Under it, above it. Oh, we know that one. What's that as a fraction? Negative 1/2. Yeah, that was on our list. All right, so we got negative 1/2 so far. The other one looked kind of goofy, so we're going to let goofy sit there for a little bit. Now, let's try the third one from the left. Okay, there's that number again. On the left side, it was 1.414, blah, blah, blah. Anybody think of it? It's actually the square root of 2. But if we don't know that, then we just say, okay, I'm going to keep going here. I've got to find another nice one. I can get this down as something I can use. So, the last one I actually probably just use the table for it, because it looks like it's one right here. But if you want to use that, yeah, there it is, 40. Second table, 40, right down here at the bottom. So, we know these two for certain should be tried with our synthetic. And then, hopefully we can get it down to somewhere where if you didn't know that was the square root of 2 and negative square root of 2, you could at least find them algebraically. So let's get started. And it doesn't matter which one you do first. This is not a horrible fraction to use for synthetic. Negative 1/2 is a nice little fraction. 4, 3, 2, 1, 0, they're all there. And just bring down that leading coefficient, but I think I'm writing too big for my space here. And just get started. So 2 times negative 1/2 would be negative 1. Add inside the box. Outside the box. Negative and a negative will make a positive, and half of 8 is 4. Negative 8 plus 4, negative 4. Negative and a negative make a positive, and half of 4 is 2. So we get 16. Negative and a positive will make a negative, and half of 16 is 8, and oh yeah, there it is. Negative 1/2, 0 absolutely works. Then, because it worked, I need to keep going. Because remember, I'm missing a couple of zeros here, and I want to be able to find them, so I'm not going to start over. I'm going to keep going with what I have. Bring down that 2 as the leading coefficient. Outside the box, multiply. Inside the box, add. Outside the box, multiply. Inside the box, add. Outside the box, multiply. Inside the box, add. Whew. The 2 that the calculator told us definitely worked. Now, why didn't we notice that last one? Because this is 2x squared minus 4. And we need to know when that equals 0. So we would add 4 to both sides. We would divide by 2 and say, oh yeah, now I know what square root of 2, 1.414, blah, blah, blah. There's the last 2. Now, towards the end of this assignment, we do synthetic with radicals. It's not as awful as it appears to be. But if you recognized it, you could do synthetic with negative square root of 2 and Remember, they always come in pairs. So we write down that we know negative 1/2 0 is a go. 4 0 is a go. Square root of 2 0 and negative square root of 2 0. Both a go. And we have all four. There they are. So we wouldn't even have to bother with the upper and lower limit test for this one. When we found all four, and they weren't all rational. We had two nice ones that could be written as fractions, but we had two irrational ones. We found them all. We don't need to go searching for any more or figuring out whether or not we have found them all. So that's really what the upper and lower bound is all about. You know, if you're not sure, do I have a bound? Are there any more out there? Then you could use that. So we're finding all those real zeros. And this one says a polynomial function cannot have more real zeros than its degree, obviously. You know, that's what we've been studying for a couple of years now. But it can have have fewer, because they could be imaginary. You know, and it happens. We get some when we have maybe a couple of nice zeros that we can find, but then the others are imaginary. When a polynomial has fewer real zeros than its degree, then that upper and lower bound test will help us know that we have found them all. We have everything that we need. So find the real zeros of this polynomial function. Prove that all of the real zeros lie in the interval from 0 to 1, and then find them. Okay, so I've got one that I need to do synthetic with, and there is some major stuff missing on this one. We have 10x to the 5th, but we don't have an x to the 4th, so we need a 0 for that. We don't have an x to the 3rd, so we need a 0 for that. A -3, a 1, and a -6. And my hope is I get all positive values, or remember 0 counts for both. So we bring the 10 down, we multiply, we add, we multiply, we add, we multiply, we add, we multiply, we add, we multiply, and we add. All positives. Good. 1 is the upper bound. Now to make sure that 0 is the lower bound. Synthetic with 0 is very nice. So we've got our 10, 0, 0, -3, 1, -6. Bring down that leading coefficient, but you multiply anything by 0 and you're going to get 0. That kind of looked like a 6 there. That's a 0. So this one is supposed to go positive, negative, positive, negative, positive, negative, and alternate forever. Positive, oh, negative. Well, remember 0 gets multiple, so it doesn't count. Positive, negative, positive. Yep, it counts for both. Negative, positive, negative. So 0 is the lower bound. Us to show that. It said, find them. Okay, so possibles. Got a 6 in the back. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Bless you. On the bottom, a 10. Ooh. Plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. And then, yeah, we could go through and we could write down all of the zeros. But in the end, we're going to grab the graphing calculator and try to be able to write those all in fraction form, but rather than spend all our time on that, we should spend it on figuring out what should we try, what is possible here in that list. 10x to the 5th minus 3x squared plus x minus 6. Well, look at that. Kind of looks like 1, 0. Let's see from the table. Nope, it's not. So let's see if we recognize the second trace. 2, like below it a little bit, above it. Oh my, 0.9505458. You guys know a fraction off the top of your head that does that? So with this one, we just have to write down to 3 decimal places what we see. This is not a recognizable fraction. So we have 0.951 was this thing supposed to have? 5. We only found 1. Well, the upper and lower bounds tell us that's where they are. And if we only found 1, we're done. That's it. So most of the time, we're going to see something that we can identify and say, hey, I know that. That's a fraction. You know, but there are going to be times where we just say, I don't know what 0.95054585 is. I'm just going to write it down and go from there. Now, because that is so nasty and we don't know exactly what it is, we can't verify that one. We can't do it. It's going to be off a little bit because of rounding when we go through there. But we say, hey, we did all we could. We found the one that's there, and we move on. So extra examples says, let's use synthetic division to find the simplified exact zeros of each of the following. Use completing the square of the quadratic formula if necessary. So if we have a quartic and 2 of them come out to be something we recognize, well, then that means there's 2 of them down there that are going to be nasty radicals. And if that happens, if you have a quadratic and you realize I'm short a couple of zeros, complete the square. Don't do the quadratic formula. Quadratic formula should just be a backup. But with this one, I see it's 2x to the third plus x squared minus 41x plus 20. How many zeros should that have? Should have 3. Look at that. They gave us a huge hint. F of 1/2 is 0. Well, that was nice of them. That means we should start with their hint. We're supposed to get a remainder of 0. So 3, 2, 1, 0, they're all there. And we know what we're supposed to get here. We're supposed to get 0. So if we make a mistake mathematically, we should catch ourselves. Bring her down, multiply, add, multiply, add, multiply. Well, that was very helpful of the book to do that for us. So at this point, we have a lot of choices. We could just say, you know what, this might be factorable. Remainder constant xx squared, so 2x squared plus 2x minus 40 equals 0. And we could at least pull a 2 out of this. And we could try factoring it if we wanted to. But most of the time we get so used to, let's grab the calculator and let's narrow down the search, you know, because we've got a 20 in the back. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5. And there's a lot of things to try. But let's see if we can get them with the graphing calculator. 2x to the third plus x squared minus 41x plus 20. Well, that might be 5. I can see the 1/2 that they gave us there, but it kind of looks like -5 and 4. Second table. Well, there it is. -5 is a 0. 4 is a 0. Let's do that. -5 and 4. Oh, I forgot to factor out the 2 out of this. There we go. And because the 1/2 worked, we would just keep going. Hey, -5. We're going to work that through here. And then my 4. Yippee! They all work. You know? But like I said, you could, at this point, say, I'm going to go ahead, it's a quadratic, I'll try and factor it. If it doesn't factor, then I'll go ahead and use completing the square to solve it. So you could have stopped after that first step and written down, you know, your x squared polynomial. How many would prefer factoring to synthetic division? So, you know, if you want to do it that way, feel free. It's algebraic, so it is verifying everything that's going on. We knew this was supposed to have 3. Found all 3, and away we go. So now, let me check. Okay, I am not going to be here tomorrow. So what I'm going to do is I am going to make a video of the remainder of these for you. because we have to still go over what happens if you do find a radical. Like now, I would hope that if you saw 1.414 blah blah blah, you'd say, wait a minute, wasn't that square root of 2? And you punch it in your calculator and go that way. So we have to be able to do synthetic with radicals and solve by completing a square when things don't work out nice. So what I'm going to do, we only have one math sub, Mr. Duskin, and he couldn't make it tomorrow. So there is not a math teacher here tomorrow. Make sure you bring your charged up Chromebook and your earbuds. I will videotape the rest of this lesson during my prep 6th hour and put it on. And then basically it's not going to be a 40-minute video. It's just not, there just isn't that much left to go through. So tomorrow in class, you could watch the video and then you could do this assignment. This is kind of day 2 and day 3 all rolled up into one here. If you wanted to, you could do some of this tonight, and then stop it. Wait, there's just one more piece that you need, and that would be the very last problem